Assalamu alaikum and hello there. Welcome to our video. Today our group will be talking about a driver system present in drivers that we had learned in modern electrical drive subject. This system is of course DTC. In this video we will cover around the significance and application of using a DTC. Next we will discuss on the principle of DTC, the control torque and flux in the system. An explanation on functionality or operation for each part of the flexi drive system will also be presented in the video. And at the end of the video, a demo will be done on how the flexi drive system obtained some important experiment result. But first, an introduction to the topic must take place. What is DTC? DTC stands for Direct Torque Control, and this control system had been used in many types of system and drivers. Proposed by Takahashi and Noguchi in the mid-1980s, DTC is one of the methods used in variable frequency drive to control the torque and speed of three-phase AC electric motors. This process involves calculating an estimate of the motor's magnetic flux and torque based on the measured voltage and current of the motor. This system offers many advantages over the use of conventional method, which is field-oriented control or FOC method, which are the important requirements especially for high power application. Next, we will move on to the significance. DTC proved to have a significance until today, as researchers push their efforts in research and searching for better system for drivers and controller. DTC is still significant in terms of improving some performance, such as to obtain high efficiency, excellent torque dynamic control, maximum torque capability for wide speed, reduced torque ripple, improved flux or torque estimation, and etc. As for the application, DTC control system was extensively used in various motor drives and applications. It is used as the main platform for the ABB inverter technology. This can be seen in 1996. ABB marketed the first DTC drive. Today, some of the components include the ABB ACS 880 industrial drive, as can be seen in this figure. Other application also includes the synchronous electric motor, which can benefit the DTC techniques in building one of these components.
Principle of DTC, direct torque control. DTC is one method used in variable frequency drive to control the torque of three-phase AC electric motors, and then involve calculating and estimating of the motor magnetic flux and torque based on the measured voltage and current of the motor. And then torque and flux can be changed very fast. Then high efficiency and low losses. The step response has no overshoot. There are no PI current control. No separate modulator is needed. And then lastly, no coordinate transform are needed. And this one is comparison between DTC and FOC. FOC is field oriented control. As we can see, dynamic response for the torque for DTC is very fast, while the FOC is fast. Coordinate reference frame use alpha beta, and for the FOC DQ. And then the low speed less than 5 nominal behavior, required speed sensor for continuous braking. And then DTC control variable torque and stator flux, and low required high quality current sensor, and the parameter sensitivity of the sensors are stator resistance, and many more. PWM modulator not required for DTC, while the FOC required. And switching frequency variable widely around average frequency, and switching losses low required high quality control sensor. And lastly, typical control cycle time around 10 to 30 microsecond for the DTC. Then next, and this one for principal control of torque. For positive torque application, both vector track their circular path and reference in counterclockwise, where the rotor flux vector always lag the stator flux vector. And then the rotor flux vector has a uniform angular frequency, whereas the stator flux movement is jerky due to apply voltage vector. Thus, the increase or decrease of torque is mainly affected by the change of stator flux. And this one is principal control of flux. 6 sectors are equal divided by 60 degree, and then 2 suitable active vectors are used to control the flux for every sector, either to decrease or to increase. Flux is controlled to form a circular locus by selecting suitable voltage vector for each vector. Lastly, 2 suitable vector for each sector can identify as the vector that have more tangential component to the flux vector. Thank you.
Okay, the left part is for DTC of induction machine that designed from Simulink, and the right part is the actual circuit that consists of level shifter and buffer circuit connected to FPGA, 3-phase IGBT gate driver, electro drive solution, fixed type inverter, and current sensor. This is for output that connected to the motor, and then the monitoring signal unit. This is for oscilloscope that we want to trace the output. And then this is for level shifter and buffer circuit connected to FPGA. The blinking blue is represent the FPGA circuit, and then the level shifter and buffer circuit is this part. But this part is represent to 3-phase IGBT gate driver. And then this is for DC diode, and this is for current current sensor. On the left part, how we want to measure that the output on this output, we will get the same value on this, and then we want to control using other software. Firstly, just after we create this circuit, we must put this part in the lookup table. Firstly, for the lookup table, we must to refer on this part. Alright, this is for lookup table for DTC of induction machine. Okay. Lookup table. Alright. Okay. let's make an example. If top stator and flux stator is 1, the section DSX is will be 101 100. From this part we refer on this part. If flux stator is 1, and then torque area stator is 1, we represent on this part. We will get the 100 for section 1, and then in section 2, if T static 1 and F static 1, which is represent to flux T static, torque status error 1, and flux stator error which one will represent 1 1 0, like this. And then in section 3, on this part, if this like this, the blue one that I bold is if flux status is 1 and torque status is 1, we will get 1 0 1 0, like this. Okay, and we'll continue to all of this part. Alright, but on other part, on this part, the sector detector, we must refer on this part. Okay, first, if the flux below than 0, alright, if the flux is below than 0, represent on this, the upper part. If below than 0, if yes, you will go straight to this part, which is this. If Q flux is below than 0, if yes, you will go to Q flux. Q flux is below than H. QH, flux H, right? Okay. Alright. If below than H, the sector will go to sector 3, which represent 3, like this. It state that if Q flux below than flux H, you will go to sector 3, and if no, you will go to sector 2, like this. Else, we will go to sector 2. And if else, if Q flux below than H, if no, which is mean no, you will go to Q flux higher than 0, we'll go to on this part, sector 4, sector 5, we'll go to on this part. If flux Q over negative H, after we complete all this part, this block part 1 2 3 4 5. Okay, after we complete all this part, however, this part is represent for HBT. HBT is the high hysteresis band, positive hysteresis band, and then this part is for 0, negative hysteresis band. That represent on this note. The upper part is positive hysteresis band and negative hysteresis bands. The lower part, that to control the frequency, the bandwidth that we don't want to over the limit. After we complete all this, by using this space, we can upload to the FPGA that control the real part of induction motor, like this one. The blinking blue one is the FPGA.
So now we're going to implement the directed control of induction motor by using the flexi drive system. So what we have here is our interface by using control desk. As you can see, there are several buttons for us to control the motor and DTC from our own PC. So now let's move on to the first button, which is the activation of DTC. This is the start and stop button, where we can start and stop the motor. For the reference torque, here we can manually adjust the torque by using this control button. As you can see, it ranges from -3 until 3. And then there is the low torque, which is set at 1, and the large torque at 2.5. This is the positive torque. And then for the positive torque, we set it at 2, and the negative torque, we set it at -2. For the plot selector, for plot 1, we use this to analyze the flux structures of the motor. For plot 2, we want to analyze the change of speed from low torque to large torque, and we want to see the effect on the torque, current, flux, and to the torque error. And then for plot 3, we want to analyze the effect of changing from positive torque to negative torque instantaneously. We also have the flux hysteresis band, where we control the gap between the upper hysteresis band and the lower band. And we also have the top hysteresis band, where we control the upper band of top hysteresis and the lower band of top hysteresis. So now what the system will control is the flexi drive, which is connected to the oscilloscope. Now this is the flexi drive. The flexi drive will be connected to the motor, which we will use the Lorenzo motor with the power of 1.1 kilowatt and Y connected. We short the connection over here. Now we move on. This is the motor and this is the load. The load is connected to the armature current, which will go through a parallel resistance of 10 ohm, which is parallel in 4. And this is the field current. Now the motor is supplied by 2 parallel DC supply, which is we want the supply to be 90 volts, so we parallel 45 and 45 volt for each one. And the field current, we use 35 volt. So now the oscilloscope, we have already done the setting. We have 3 kind of setting. As I explained, for plot 1, we can use setup 3, which is we already put in the memory here. And for plot 2 is for setup 2, and for plot 3 is setup 1. So let's get started. To start off, we will select plot 1 for our experiment, and then we press start to start the motor. As you can hear, the motor is already started. Now, as you can see, there's a toggle button for the plug hysteresis band. We control the hysteresis band from small, medium to large distance between the band. So now we are at the smallest bandwidth between the band, and let's see the effect on the flux locus. So now at the smallest hysteresis band, you can see that the flux locus is nice and round. Now when we change the hysteresis band to the middle band, we should see the flux locus is starting to look a little bit not smooth. As you can see now, the flux locus has shown more vector than it has before from the smallest hysteresis band. And now we're going to make the bandwidth even larger by selecting the maximum for the upper band and the lowest for the lower band. Now the flux locus has now become more unsmooth, and the vector can be really seen inside this graph. As you can see, when the smallest hysteresis band, the smallest gap between the upper and lower hysteresis band, the flux locus is smooth and round. And then when the largest bandwidth between the upper band of hysteresis and lower band of hysteresis, you can see that the vector is already shown their selection. Now this is the result we obtain when we change from positive torque to negative torque. You can see that from the positive torque, which is at positive 2, drop down instantaneously to negative 2 of the negative torque. Now why we change from positive torque to negative torque is to instantaneously reduce the reference angle between the stator frame and the rotor reference frame. As you can see, when we zoom in into the graph, you can see that the flux will also decrease rapidly and then increase back from 0. It will drop from 0, drop down, and will rise back up to 0, and then we will oscillate between 0 and negative 1. So this is more practical than changing from large torque to low torque, because the reference frame will instantaneously drop down faster. Next, for the last plot for the direct torque control, we want to use plot 2, where we will observe the change from low torque to large torque. So now the experiment will run at low torque, which is at 1, and when we change to large torque, it will be at 2.5. Now as you can see, the motor is running at low torque. Now we will change to large torque. The speed of the motor will increase because you have more torque. So now when as you can see in the oscilloscope, this is the current waveform and the torque waveform. When the torque is increased, the current will also increase. But the specialty of DTC is when we increase the current, we also limit the spike of the current, so it will not be large enough to disturb the motor. Now let's see when we want to change from flush torque to low torque. We have to first input the menu here, and we have to choose the slope to be decreasing. So after we set that, we move on back to the interface. As you can see, the motor is running at large torque. Now we change to low torque. As you can see, when the motor is running at large torque, same as before, you see the torque is high and the current is also high. But when we change to low torque, you can see the current is also decreased with the torque.